We'll take a look at the ions and then we'll come back to the if you have a question about that. But what ion did we leave off with? Talking about calcium. Chromium? Okay. So we didn't, did we finish chromium or we haven't started? Finished? Okay, then after chromium, what comes next?
Calcium.
Calcium? Okay. So let's take a look at the calcium test. So let's say our original unknown contains calcium. When we add the HCl here, there should be no reaction. Calcium 2 plus is not going to react with H plus or Cl minus and R. Then we take this solution 1 and then we add the ammonia and we should get no reaction here. Calcium 2 plus, plus the ammonia plus the water doesn't precipitate anything. Normally we would expect a hydroxide precipitate, but in this case we don't, because hydroxides are all insoluble except for group 1, ammonium, and calcium, strontium, barium. And so this we get no reaction, there's no precipitate here. And then 3, I'll take this solution 2 and then add what to it? Ammonium oxalate? And we should get a white PPT for this. PPT. That is calcium ions, like oxalate ions. And this results in a precipitated calcium oxalate solid. It's a metathesis reaction. Okay, and then what do we add? This. HCl? Okay. So 4, we'll take the precipitate from step 3 and then add HCl. This is going to give us a CCS, a clear colorless solution. Because calcium oxalate solid plus 2H plus yields calcium ions plus oxalic acid. So this would just be a metathesis, stronger acid to weaker acid type deal. Okay, after this, what do we do? Flame test. So we'll take solution 4 and do the flame test. And we should get a short-lived brick red flame. This is the brick red color. That's it. This you have to be very careful with contamination. If there's just a trace of sodium present, it's going to drown out the brick red color and you'll never see it. And so we got to make sure that the platinum is very clean, that there's no color. If you want to see what the brick red looks like, this brick red, we have calcium chloride. Hopefully it hasn't been contaminated. But in the dropper bottles, you'll find some calcium chloride or calcium nitrate. You can test that directly in the flame and see what color it should be. If those have been contaminated, somebody accidentally putting something in there like sodium ion or whatever, then it'll be hard to see. Hopefully they haven't been. We want to avoid unintentional cross-contamination. of your solutions, and sodium is one that's easy to cross-contaminate, so we have to be very careful with this. Others just naturally become contaminated. For example, barium hydroxide. You know, if you look at the bottle of barium hydroxide, there's a white PPT in there. And each time you clean the white PPT, you get more white PPT. And so do you know, when we look at the barium hydroxide, what or who's contaminating that? You know, who's contaminating the barium hydroxide? It is easy, it's air. Air is contaminating our barium hydroxide. What in air is contaminating our barium hydroxide? Not oxygen, something else in air. Barium hydroxide is a base, you know, it's a strong base because all soluble hydroxides are strong bases. So, is there an acid in air that reacts? Is there a Lewis acid in air that reacts? The answer is yes, there is. It's CO2. CO2, you know, when barium hydroxide reacts with CO2, it forms barium carbonate, which is the white precipitate in H2O. This is a Lewis acid-base reaction. And so this kind of contamination is the only way you can prevent it is just not expose it to air, but that's not an option here. In some labs it is an option, you know, they can do things in the absence of air. In the absence of air, they use other gases, you know, store it under. But anyway, hopefully our calcium, at this point in the analysis, there should be no sodium. The sodium would have been washed out with the other decantates or supernatants. And so we should just be left with calcium 2+. Forgot to do this in the morning, which goes to calcium 2+ in the gas phase, which is going to be reduced in the flame to calcium, the element, and then excited to double dagger, and then drop back down to the ground state plus photon of light. So that should be it. So if we get that brick red flame, then that would be the positive for calcium. Okay, after calcium comes what? Zinc. Let's try Zn2+ test. If our original unknown contains zinc, then the first step is we're going to add the HCl to it. And with zinc, we expect no reaction. That is, Zn2+ won't precipitate or form a gas or do whatever here. And then we take our solution from step 1 here and then add ammonia to this. Okay, we need ammonium here. This is important. And we get NR. In reality, we should get a precipitate because zinc hydroxide is insoluble. And so if we have hydroxide ions present, which we do when we have ammonia and water, then I expect to find a white precipitate of zinc hydroxide and 2 ammoniums. And so what we're going to do here is we're going to do this Le Chatelier's thing. The Le Chatelier's thing is we're going to make sure that we have a little bit of ammonium in here. If we got just the right amount of ammonium, it's going to shift this left. And so Le Chatelier's principle, if we increase the concentration of the product, it's going to shift the reaction to the left. If we shift it far enough to the left, we'll get no reaction here. And so the shift left prevents precipitate from forming. Well, we have to be careful, because if we shift it too far to the left, then we aren't going to get the 3+ cations to precipitate. And so it's kind of a delicate balance here. Make sure. All right, so we should have gotten a precipitate, but we prevented the precipitate from forming. Why? Because we didn't want zinc 2 plus to contaminate our iron, chromium, and aluminum. Okay, what's the next step? Well, the other, wait, before I get back to this, ammonia is used to precipitate out hydroxides, but also ammonia is used to complex metal ions too. So Zn2 plus ammonia as a ligand might form something like the tetraamine zinc ion, the zinc 2 ion. Does the tetraamine zinc 2 ion form? Or not? How do you know what complexes form? How can you predict? Because ammonia could react in different ways, you know. Hard, soft, yeah, that's it. It's the hard, soft. We have to use, you know, MO theory and all that other stuff. It's not so easy to predict, right? Since hard, soft, acid, base, HSABs, way back from week 1 in the PowerPoint, in MO theory, that's kind of beyond the scope of our class, so we're not going to make predictions. We're just going to look it up in Appendix D and C. You know, does zinc 2 complex with ammonia? Yes or no? And so it's different, you know, some stuff. You know, eventually, you know, after looking at all that data, you know, maybe you'll see some kind of reaction pattern, you know, pattern and reactivity. And then you might consider, you know, why doesn't it? You know, why do these other things form amine complexes, but zinc doesn't, like cobalt? Well, cobalt or chromium, you know, those form nice amine complexes. But that comes later. 3. Okay, then what? Yeah, then we're adding ammonium oxalate. So it's solution 2 plus ammonium oxalate. What should happen to the zinc? Will the zinc precipitate out as zinc oxalate? Yes? Do we get zinc oxalate? White PPT? You can just look at the flow chart and see. Precipitate? No reaction. And so why is it, you know, we have Zn2 plus oxalate. Why don't we get a precipitate here, you know? Why do we get a precipitate with calcium 2 plus and not zinc 2 plus? Should I bring up HSAB, hard, soft, acid, base? LCAO, linear combination of atomic orbitals, MO, molecular orbital. Well, in this case, it's likely because of the lattice energy, right? So what you do is you memorize these solubility rules. You memorize solubility rules like, you know, hydroxides are insoluble because of group 1 and ammonium. Group 1 and ammonium and calcium, strontium, and barium. All the other hydroxides are insoluble, right? And so you memorize that over and over again, right? And pretty soon, you have it down. You know, you have it memorized. But then you start to think, well, that's not enough anymore. You know, it's like this kind of escalation. It's like, you know, if you had a fear of roller coasters, right? And then you start riding the little roller coaster, pretty soon after the 100th or 200th time of riding the little roller coaster, it starts to get a little bit boring, right? And so you start thinking, well, maybe you want to do something more challenging. Well, the same thing here. You know, after you start memorizing this, you go, well, I have it down, but isn't there more to it? And then you start thinking. You start thinking like things like, why is magnesium hydroxide insoluble but calcium hydroxide soluble? And why is that? Because of what? Lattice? Lattice energy, yeah. And so here, it's likely because of the lattice energy. Magnesium is smaller, right? It's got the same charge, so it's got a higher positive charge density, which means it's going to form a stronger, what kind of bond? Ionic bond, stronger ionic bond. And so here it's likely due to lattice energies. Whereas when we're looking at like complexes, like, you know, will the mean, rather than trying to precipitate out the hydroxide, will the mean attack the zinc as a complex and form an amine complex, right? That's more covalent bond, right? Because we have the coordinate covalent bond. And then some things are like this. Some things are like, well, these are +1, and +1, you know, these are pretty unreactive with any anion. And so they don't precipitate out, but silver's +1, and that precipitates out with lots of stuff. So why silver, which is +1, behaves so differently than all these others that are +1? Why is that? And so, like, you know, +1 like ammonium in the group 1. Well, silver is a little bit different because silver is a what we call a heavy metal, or heavier metal. And when we're dealing with heavy metals, is the bond more ionic or is the bond more covalent, or what? Is there? Yeah, the bonding is much more covalent, and there we have to look at, you know, MO theory, LCAOs, hard, soft, acid, base. And so those are more difficult to predict. And so these are the types of things that you start thinking about, you know, after you start trying to learn the patterns. Well, let's continue on. So likely it's because zinc is doesn't have as strong of a lattice, you know, as these guys do. And the same thing here. Calcium hydroxide is likely soluble because it doesn't have as strong of a lattice as magnesium hydroxide. Beryllium hydroxide, what would you predict for beryllium hydroxide? Soluble or insoluble? Insoluble. And even stronger lattice or weaker lattice than magnesium? A much stronger lattice. In fact, beryllium you don't hear much about because beryllium is extremely toxic. Right? Because beryllium is very reactive as an ion. If you have beryllium 2+, then it can easily displace magnesium and calcium in the body. And so we need magnesium and calcium for proper functioning of whatever biological systems. But if beryllium gets in there, it screws everything up. So we don't work with that. Okay, let's go on here. Actually, beryllium's still used. You know, beryllium used to be used in the aerospace industry. This is a lightweight metal, which has, you know, strength similar to magnesium. And so a lot of people are thinking it's perfect for airplanes. Until the people who are machining all the beryllium, all of them died, you know, from beryllium poisoning. And so it's no longer used, but it's used in, you know, where it's used? It's used as an X-ray window. You know why they would use beryllium as an X-ray window? X-rays are electromagnetic radiation, and so what in matter absorbs electromagnetic radiation? Do the protons absorb electromagnetic radiation? Not really. Do the neutrons absorb electromagnetic radiation? Not really. The primary thing that absorbs electromagnetic radiation, or light, are the electrons. And so beryllium has so few electrons that it's not going to absorb much electromagnetic radiation, making it a good window. It's a metal. It's a metal, you can't see through it visibly, but with X-rays, this passes right through. Lithium, lithium has even fewer electrons, right? And so lithium would make a better X-ray window, except for one thing. Lithium is very reactive. Lithium is at the top of the activity series, so you wouldn't use it because if you splash water on it, it'd catch on fire, basically. Whereas beryllium, if you splash water on that, it's not going to catch on fire. And the remaining two are gases. So beryllium makes an excellent X-ray window. What makes an excellent X-ray barrier or X-ray shield? Yeah, you want something with a lot of electrons, like lead. Lead has a lot of electrons, so it can absorb a lot of electromagnetic radiation, like X-rays, right? But why not something that has even more electrons, like uranium? If you use uranium, has a lot more electrons, right? Which is 92. Where's element number 92? Or Neptunium. Well, uranium is good. It's solid. Neptunium is gas. Unfortunately, these are gases. So it looks like the uranium, which is solid, at element number 92 is perfect because it has a lot of electrons, right? Obviously not. So you aren't going to use uranium, or you aren't really going to use any of these others because they're all radioactive. That leaves us with lead. So lead makes an excellent X-ray shield. All right, so 4, what are we going to do after we add the ammonium oxalate? Sodium hydroxide? We add the sodium hydroxide to solution 3 plus sodium hydroxide, and we just end up with a CCS. So basically it's going to look like nothing happened, right? But did something happen? Yeah, what happened? Are we going to get zinc hydroxide PBT? No, we're going to get, yeah, tetrahydroxozincate 2 ion. And so we're going to complex it. Why didn't it bind to 6 hydroxyl ligands? Well, that's not what is observed. You know? There's got to be a reason for that, but we don't know yet. We'd have to dig deeper into it. So it complexed with hydroxyl, but it didn't complex with amine. Why is that? Well, that's just what's observed right now. We'd have to get into the whole molecular orbital business to more properly understand it, which we aren't going there. Yeah. All right, so now we have the tetrahydroxozincate 2 ion. What are we going to do next? Potassium hexacyanoferrate. Okay, 2 and an HCl. So we're going to take solution 4 and then add the potassium. We've seen this before. Hexanoferrate and then some HCl. I'll put HCl here, or you can put it as a reactant. And then we should get a precipitate. What color is the precipitate? Gray-green precipitate. Gray-blue? Gray-blue precipitate. So what's happening here? Well, the HCl is actually reacting first. So the tetrahydroxyl complex is destroyed, right, with the HCl. So we need 4 H pluses. It's going to free up the Zn2 plus and make 4 waters. Okay, once the Zn2 plus ions are freed up, then they can react with the complex. This is kind of a strange metathesis reaction. You can see why I call these metathesis rather than double replacement, because this reaction doesn't fit the double replacement form. Because in this reaction, how many zinc ions need to come together? How many zinc ions? Well, what's the product? The product is going to be Zn2, K. Is there potassium there? What's the precipitate formula, the gray-blue precipitate? The formula is Zn3, K2, solid. This is a precipitate. This is what we call a mixed cation salt. Mixed cation salt. So double replacement doesn't work here because this would be something like a triple replacement or something like that. It doesn't work. And so what we're doing is we're just bringing the ions together. And so we have 3 zincs plus 2 potassium ions plus 2 hexacyanoferrate, 2 ions. Gives us that precipitate. This is ion combination reaction, or metathesis. Okay, so if we get that gray-blue precipitate, then we have a positive test for Zn2+. Our original one down. All right, after the zinc, what ion are we going to look for? Magnesium and nickel. Okay, which one comes first, magnesium or nickel? Nickel? Okay, let's take a look at nickel. Next. Did we miss any? No? All right, so we're going to do nickel 2+, the test for that. So if our original unknown has nickel in it, and we add the HCl, we get NR reaction. And so Ni2+ won't react with H+ nor chloride. Therefore, nothing happens here. 2, we'll take the solution and then add the ammonia / ammonium to this, and we get NR. But really, nickel hydroxide is insoluble. Do we complex nickel? So here we got Ni2+ plus 2 ammonias plus 2 waters yields nickel 2 hydroxide solid plus 2 ammoniums. And so this stuff wants to precipitate out, because nickel 2 hydroxide is insoluble, and therefore precipitation is a driving force for this. And so the way we're going to prevent it is the Le Chatelier's principle. We're going to drive up the ammonium concentration and shift this left. To prevent precipitation. The only thing we want to precipitate out with ammonium are the 3+ cations. The more soluble 2+ cations will stay in solution because they don't have as strong of lattices. The bonding isn't as great. All right, then with this nickel 2+, what are we going to do? So we'll take the solution from 2 and add what to that? Ammonium oxalate. And we get an R again. And this is weird because this is another 2+ cation. But this 2+ cation doesn't seem to like oxalate either. And so it seems oxalate is kind of particular about what cations it reacts with, right? And so in order to investigate that further, we'd have to look at the bonding involved in there, or the lattice, and see what the lattice energies look like. Okay, after the ammonium oxalate, what are we going to add? Sodium hydroxide. So we'll take solution 3 plus sodium hydroxide. And do we get a complex? Should we get the tetrahydroxynickelate too? No. No. Why don't we get that? Why don't we get the tetrahydroxynickelate too? What would your answer be? Yeah, right. It's hard to predict because we need to look at it more deeply. What do we get here though? Well, nickel hydroxide is not white. Nickel hydroxide is green. We get a green precipitate. And so nickel 2+, rather than complexing to form a tetrahydroxo, it's actually going to just precipitate out as a hydroxide. So we get nickel 2 hydroxide solid, green PBT. This we call a positive test for nickel at step 4. That's a positive test for nickel. It's not the positive test for the nickel ion in our unknown. It's just, you know, if we get a green PBT, then that means we had some nickel in there. What would be a negative test for nickel at this point? At step 4, what would be a negative test for nickel? Yeah, the green PPT disappears. If you see no green PPT, that would, you know, a negative positive test. And so the book has some weird terminology with this, and so you're going to have to deal with this in the test for magnesium. Okay, after this, what do we do? Here. 15 molar ammonia. So to the green PBT, okay, and so this will be the precipitate from step 4 plus ammonia yields what? A violet solution, because what forms? Hexamine nickel 2. Hexamine nickel 2, which means that nickel does, oops, this is not right. Sorry, it forms a violet solution. So what we have here is nickel 2+ plus 6 ammonias yields hexamine nickel 2, which is a complex. Well, this is a 6-coordinate complex here. How did you know? You probably didn't. Could you have predicted it? No. Stuff is difficult to predict because you need all that MO stuff, MO theory. But let me ask you this. Compare step 5 with step 2. Step 5 with step 2. Why didn't we get the hexamine complex forming in step 2? Okay, that would be a competing reaction. And so actually there are 2 competing reactions. Nickel 2 could have reacted with the ammonia-water combination, or nickel 2 could have just reacted with 6 ammonias. If nickel 2 reacts with 6 ammonias, we form this. Why didn't we form this here? Okay, 1, we had excess ammonium, and 2, this is an important reason as well, 2, because well, let me ask you this. What concentration of ammonia do we use in step 2 here? 6 molar? What concentration do we use in step 5? 15, so that gives you a clue. The other reason we don't form this is because we're going to have a low concentration of ammonia, which is going to shift this back. It doesn't mean that none of this complex might form and we might lose some of the nickel. Here. And so this is another reason to keep the ammonia low at this point here. We don't want it to go too high. And so this is a side reaction that can take place. And hopefully we can minimize that. Otherwise that'll result in loss and also could complicate our subsequent analysis. All right, after we form the hexamine nickel 2, what do we do next? Well, now this they talk about the negative test for nickel. What the heck do they mean by negative test for nickel? I get asked this question every semester. So what does that mean? Until you get a negative test for nickel. So we add the ammonia until we get a negative test for nickel. What the heck? Is that what it says? Add the ammonia until you get a negative test for nickel. What is a negative test for nickel? Until the green is gone? Yeah. Yeah. So I wish they wouldn't have said negative test for nickel. I just would say, you know, if they would say until the green precipitate disappears, that would be good, right? Because when you know the green precipitates disappeared, then you know you... Actually, I didn't write this equation correctly, did I? I'm not adding it to nickel 2 in solution. I need to... Sorry, fix this. I'm adding it to the precipitate. I need to destroy this precipitate by adding concentrated ammonia. And this precipitate gets destroyed and frees up the 2 hydroxides like that. And so I need to watch that precipitate disappear. And it's easy to do because of the color. The other precipitate we have in there is white, so can't get them mixed up. Okay, then what? Okay, dimethylglycine? DMG for short. Just call it DMG, dimethylglycine. You add DMG. DMG is a coloring agent. And then what? DMG is like a dye. We used a dye before. Do you remember what it was? Aluminon. And so DMG is the same kind of thing. It colors a precipitate by introducing a small amount of impurity in there. And so what else are we adding at this point? Just DMG? Oh. Then DMG is not a coloring agent. DMG is actually a precipitating agent. And so what are we going to form here? Do we have to destroy the complex in order to get it to precipitate? Are we adding any acid, like HCl? No, we're just going to add the GMG straight to this? Okay. And so we'll take the solution from 5 plus DMG. And what color precipitate are we going to get? Strawberry red precipitate. Okay, and what's the reaction here? Mm-hmm. Right, you can see what the formula for DMG is. And so you'll take the hexamine nickel 2 plus the C, what is it, C4, H7, N2, O2 minus, 2 of those, and then you'll form the Ni parentheses C4, H7, N2, O2. Quantity 2, solid. Okay, so once you get that red precipitate, then that's the positive test for nickel 2. Okay, what's the other step? What's the other ion we're doing? Magnesium. I think in the magnesium analysis, we're going to make some ammonium nitrate. Have you heard of ammonium nitrate? Yeah. So I'm going to show. Do you know the ammonium nitrate? Caused the worst industrial accident in the U.S. Have you ever heard of it? Texas City. And so let me show you Texas City here, if I can find it. This morning. That's not the one I want, sorry. Is there a history for YouTube?
You can't spend much time in Texas City with all...
All right, this is it.
You can't spend much time in Texas City with all the big ships that come and go, the oil and chemical refineries, the pipelines and storage tanks brimming with flammable products. You can't spend much time here without thinking the unthinkable. Could it happen again? Could Texas City be another boom town in the worst possible way? Years ago, Texas City burned its way into the nation's conscience. The worst industrial accident in American history made Texas City synonymous with disaster. The day it happened, Will Lane was very near the epicenter.
It was very strange. I'm real glad to be alive.
Lane was a young chemist at the Monsanto chemical plant. He remembers seeing the bright orange smoke from a burning ship. Firefighters were busy pouring water on the French freighter Grand Camp at the city docks across from the Monsanto plant.
You could look at it, it was real pretty to watch. And there were townspeople by the hundreds that lined the part of our parking lot that was nearest to the ship. They came down to watch a fire.
Texas City had a new fire truck, and this was its first day out. 27 firemen were on the docks trying to put out the fire. The burning ship was so hot, the water around it was boiling. But as a chemist, there was something about that orange-colored smoke that worried Will Lane.
We get to see bits and pieces of paper bagging going up in the air and away, and my boss thought, and I thought too, that we were witnessing a nitrate fire, but someone had said it's a grain ship, and the grain is on fire.
So believing it was only a matter of time before the fire was out, Will Lane went back to work at the Monsanto lab. But the fire was growing hotter, and the orange smoke was attracting an even larger crowd along the docks.
It was a very, very strong sulfur in the air, sulfur fumes.
Herb Metzger watched the fire while talking to a group of high school kids.
This smoke was just a beautiful orange.
Mary Hunter, a Monsanto secretary, was watching from her office window.
And across town, Mrs. Knappenberger, a housewife with a home camera, came here to the Texas City dike to get a closer look at the burning ship. She didn't know it then, but she was about to record America's greatest man-made disaster.
The ship had been loaded not with grain, but with ammonium nitrate fertilizer, the same ingredient that would be used years later in the Oklahoma City bombing. The Texas City blast was so strong it registered as an earthquake in Denver, 900 miles away. It created a tidal wave that washed a barge into a parking lot. 2 airplanes circling the ship were blasted from the sky. Flying debris punctured chemical storage tanks, creating an even larger inferno.
We have another truck up here off the road. It had about 10 or 15 men, and they were all crushed.
The explosion killed at least 581 people, including school children who had come to watch the fire. But the danger was far from over. Tomorrow, we'll hear the stories of survival and courage from the people who were there 50 years ago. Charles Hadlock, This is Charles Hadlock. Texas City has tried to outlive its past, but it's hard. There are so many reminders. An anchor here, a propeller there, and sad, sometimes painful memories all around.
Even today, 50 years later, the tragedy is not forgotten. 6th Street, the once busy main street of Texas City, has been renamed the Street of Memories. For it was along this street that so many screamed and ran for their lives.
The explosion of the French freighter Grand Camp left an entire town dazed and confused.
And I ran as fast as hard as I could.
There are many stories of survival. Dr. Will Lane was in the Monsanto lab. He had been watching with suspicion the bright orange smoke of the burning ship docked next to the plant when it suddenly exploded.
And when the lights just went out, I could not see more than 2 or 3 feet. And I thought, my God, it was a nitrate explosion. I'll probably lie right here and be burned to death.
He got up, looked over his shoulder at the burning tanks of benzene, and ran for his life.
Passed a car in which 2 people had been decapitated. Then I passed one of the 2 little planes that had been flying around overhead, came down along the path that I took up into town.
I'm sure all of that glass came into us, and I must have gone like this and so my arm was injured all in here.
Mary Hunter was also in the Monsanto plant. To this day, she still has shards of glass in her body.
I had it cut out of me, but luckily it had lead in it, and therefore when they x-rayed it, they could find the glass.
Before the explosion, hundreds of people were on the docks, including Herb Metzger.
I had turned to walk away. I had my back to the explosion, but the force hit me in the back, and it sort of just, I don't know, I would say it picked me up, but it blew me forward 20 or 30 feet.
Suddenly, pieces of the ship were falling all around him. He crawled under a car.
A couple of pieces hit the car. I could feel it, you know, and it jarred, but nothing hit me.
Here comes another explosion. But pieces of metal did hit the High Flyer, a second ship loaded with ammonium nitrate. Efforts to tow the burning ship out to sea failed, and 14 hours later, it exploded. The fires burned for days. Nearly 600 people died, and 5,000 were left injured or homeless. Those who survived helped each other.
Well, we had to pry some folks out that had telephone poles, in fact, I guess, or some kind of big poles blown across them. And they obviously were crushed, you know. It was not a nice sight, but kind of steeled myself to it for a while.
Even after the dead were buried, many survivors never talked about it again. But over the half-century since the explosion, they rebuilt their lives and their city. That must have been a hard thing to do, with so many memories around. Charles Hadlock, 11 News, Texas City. This is Charles Hadlock.
So what makes ammonium nitrate so dangerous? Ammonium nitrate is not stable, and it could decompose quite violently. When it decomposes, well, the reason it's not so stable is because ammonium. When you think of ammonium, it's like you know, I was on the internet yesterday and I saw the website and it said you know, common household chemicals that you should not mix. It's like 10 common household chemicals. You know, and one of the most common ones that people say, do not mix chlorine with, or bleach, you know. You do not mix bleach with Windex. Don't mix bleach and Windex. Why? Because Windex contains ammonia. And ammonia is a base, and bleach is bleach is mostly sodium hypochlorite. Is a what? An oxidizer. So yeah, don't mix a base with an oxidizer. Why not? Well, it's not because of ammonia's base properties. It's because of ammonia's redox properties. When you look at ammonia, what comes to mind as far as redox goes? It's a good, or it should be a good reducer. Yeah, ammonia, you know, is electron rich. It's got -3 on the nitrogen, so we say that's a good reducer. So if you mix bleach with ammonia, you're going to get a redox reaction. Redox reactions, you know, it's hard to predict exactly what the products are, but it's likely you're going to generate some toxic gases here. And you could potentially have an explosion depending on the concentrations, right? And so there have been many, you know, plumbing or in-sink explosions, like people mix chlorine and bleach down the sink, and then they'll hear some gurgling, because gases are being formed, and then all of a sudden it gets hot enough, and then they'll get a face full of whatever products or whatever bleach is unreacted or ammonia is unreacted. It'd be a nasty reaction, but that's okay because we can prevent it. How do you prevent it? You just don't mix them together, right? But in ammonium nitrate, unfortunately, they're already mixed together. Because ammonium is what we call ammonium is just like ammonia. When you look at, even though this is an acid, that's a base, when we look at the redox is the same because nitrogen is -3. So redox-wise, ammonia and ammonium are going to behave the same. And so this is electron rich. That's what we call a reducer or fuel. Nitrate is electron poor. And so this is what we call an oxidizer. And so unfortunately, in this, it comes pre-mixed. You have your ammonium bleach mixture, kind of same type of scenario, except rather than ammonium bleach, we have ammonium and nitrate. Well, ammonium and nitrate, as long as they stay separate, now they can stay separate when they're in a solid lattice, because in a solid lattice, you got your ammonium ions here and your nitrate ions here, and they just vibrate, right? But what happens, if you start heating it up? If you start heating it up, those vibrations get bigger and bigger until finally the ammoniums and the nitrates can collide and react. And once they get hot enough, they're going to collide and react, and then you see what happens. The Grand Chem and the other shit. And so you guys are making this, and so we should be aware of this because we don't want a mini Texas City happening in lab, right? You got to be careful. And so let's take a look at where this stuff is being formed. Is it in this magnesium analysis or not? So let's finish this up here. And so the next ion is magnesium 2+, is that correct? Or did I skip one? No, it's magnesium 2+. All right, and so in step 1, if our original unknown contains magnesium 2+, and we add the HCl, we expect no reaction. And that is, magnesium ions don't care for H+ nor chloride, so we get NR. In step 2, we have magnesium ions plus ammonia/ammonium. This gives us no reaction here, although it should give us a reaction because magnesium 2+ plus 2 ammonias and 2 waters, this should precipitate out magnesium hydroxide, solid, and 2 ammoniums. But again, we're going to prevent this from happening by increasing the ammonium and shifting this to prevent precipitation. Okay. Then we go to solution 2 in the ammonium oxalate. Is that correct? So solution 2 with ammonium oxalate yields no reaction. So that means the magnesium 2+ plus oxalate, that's weird because, magnesium should be similar to calcium, right? And so why do we get no precipitate here, or do we get a precipitate? Does a little bit of precipitate form here? Do we get some magnesium oxalate or nothing? Some? None?
Yeah,
A little bit? So let's put a little asterisk here. Well, let's continue. Most of the magnesium should make it through, hopefully, and then we get solution 3, and then we add what to that? We add nitric acid. Oh, do we want to add nitric acid to ammonium? Because ammonium is a good reducer. Nitric acid is a strong oxidizer. And so, we got to watch out, because if we add nitric acid to ammonium, that could be dangerous. It'd be like adding nitric acid to ammonia. And so to this solution, 3, are we adding nitric or HCl first, or what are we adding first? Nitric? We add HCl first. So we add HCl and then we heat it, right? We heat it to evaporate the water. Heat it to dryness. Residue. And so what's happening here? Well, the HCl doesn't react with magnesium ions. We have the HCl in there to react with ammonium ions, right? And there's chloride present, and so when we heat this to dryness, we should form ammonium chloride, solid. Once all the water is evaporated, then the ions will come together and form a crystal, or precipitate. And then what do we do with ammonium chloride? Actually, I'd like to get rid of all the ammonium if it's possible before adding the nitric acid. And so what happens here if I heat ammonium chloride? Will it decompose? Will it decompose? Hopefully, what do you think this might decompose into? Ammonia and... If you subtract ammonia out of there, what are you left with? Hydrogen chloride gas. And so hopefully it decomposes into these, and those get vaporized off, and then I can add the nitric acid. And so I want to kill off most of my ammonium. And one way to kill it off might be to add the HCl there. Right? Okay, then what am I doing? I'm going to be adding the nitric acid now. And so to this residue, and so I'll just call it a precipitate from 4, I add the HNO3. What concentration of HNO3 am I adding? 16 molar. 16 molar, isn't that that's dangerous, right? I mean, the more concentrated it is, the more reactive it's going to be, and the more violent the explosion should be that results. So we're adding 16 molar. If there's a lot of ammonium present, that's very dangerous, right? And so hopefully there's not a lot of ammonium present. In fact, hopefully there's none, but apparently there's going to be a little left over, isn't there? Because what we're going to have here is we're going to have this, and then we're going to heat it to dryness again. Not only are we heating it to dryness, but we want to continue heating it. You know, this dry residue we heat, you know, to decompose. And so it's hard to tell if it's decomposed. You know, what you should see are fumes. This is going to be the indication that some decomposition is happening. Fumes. And the same thing here, dry residue, we continue to heat this, and then it'll start fuming. And so what is that dry residue that we're going to have there? And so our precipitate, you know, our precipitate might be some ammonium chloride or whatever. And then when we add the HNO3, what happens is the HNO3 doesn't react just yet because it's just going to dissolve the ammonium chloride. So we have ammonium chloride AQ. And then we continue to heat this until it turns into a dry residue of ammonium nitrate, solid. And then do you want to keep heating the ammonium nitrate solid? No, I mean, they were trying to cool it down. You know, that's why they're spraying water on it. You know, the brown, the orange gas that was coming off the ship was NO2. NO2 is a brown orange gas. And so what you might see is, wow, if you heat this up, you might see some brown orange gas come off that shit, or out of your evaporating dish. Do you want to do this in the middle of the bench? No, you want to do this in the hood. And even if you were to do this in the hood, you probably want an explosion shield, right? At the very least, wouldn't you? And so what are you going to do with this ammonium nitrate? You're going to continue heating it. Does that sound right to you? No, it sounds awfully dangerous to me. If you have ammonium nitrate and you continue heating it, then you could potentially have an explosion. And ammonium nitrate, when it decomposes, it can decompose into different things depending on what the temperature is and other factors. But in this particular case, under these conditions, we should form some gases, and those gases are going to be nitrous oxide gas and H2O gas. So is this balanced? Let's check. 2 nitrogens, 4 hydrogens. We'll need 2 waters. 4 hydrogens and 3 oxygens, 3 oxygens. And so we're going from a small amount of solid to a huge amount of gas. We got 3 moles of gas coming from nothing. And 3 moles of gas is going to be about 75 liters. So all of a sudden, the volume goes from a small, I mean, if we had a mole of ammonium nitrate, we're going to have a lot less. It's going to go from small to very big. And if it goes from small to very big, very fast, you get a detonation, you know, shock wave. The shock wave moves faster than the speed of light. And then there's a real explosion. Sometimes it's slow or slower. So hopefully this is very slow. You know, if we generate this very slowly, then we aren't going to get this big shock wave, mechanical shock wave. Uh-huh.
Is this an extra step you want us to take, or I don't see it?
You don't see it in the lab manual? What was 5A? For zinc?
No, 5A is like
Separation and detection of zinc. Why do we want to get rid of the ammonium in zinc? All right, so this was a step that doesn't belong here. Is that what you're saying? Okay. And so we have to insert it into the zinc analysis. In the zinc analysis, where does it come in? In the zinc test. After the ammonium oxalate? Okay. So in the zinc test, we had the solution plus the ammonium oxalate yield NR. What number was this? 3. Okay, then we go to 4. Now we got to get rid of all that ammonium. How do we do it? Right, and so we go over here. Do we add the HCl? Yeah? And so we add the HCl so we get this dry residue and then continue heating, hopefully destroy a lot of the ammonium chloride. Then we take the residue from step 4 and then add HNO3 get a dry residue. That dry residue can contain ammonium nitrate, and then we're going to keep heating it. And so in this case, you know, we recognize that this is very dangerous, so why are we doing this? Well, you guys can opt out, or you can just have your partner do it. You know, this is a good step for your partner to do, in case it blows up. But you know, these redox reactions all depend on the conditions that you do it. You know, methane can cause big explosions as well. And so under these conditions, the amount of ammonium nitrate we have is very little. It's so little that we aren't going to see a mini Texas City in your beaker. Unless you skip a step or something and then start adding the nitric acid directly, you know, and you have a lot of ammonium. If you have a lot of ammonium in there and you add the nitric acid, then you're going to see a mini Texas City. But as long as you follow the procedure okay, you should be okay, and we don't have to worry about an explosion. All right. But still, you know, I cringe whenever I think about heating ammonium nitrate. You know, it seems like a ridiculous thing to do, a ridiculously dangerous thing to do, is to heat ammonium nitrate. Okay. Why do they do it? Because it's an easy way to kill off the ammonium. You know, ammonium's a reducer, nitric acid is an oxidizer, you can get rid of it easily. And you just got to do it under, you know, mild conditions, that is, you know, low concentrations. Well, you look at it, 15 molar, is that low? No, that's high concentration. And so we aren't doing it under low concentration, we're doing it under small amounts. And so if you have just a very tiny bit of ammonium nitrate, then you aren't going to get much of an explosion. In fact, you're getting no explosion. And so it's just because maybe in this step we get rid of most of the ammonium, the ammonia gas goes out in the hood, and so we just have a tiny bit of ammonium in there. Because if this were a significant quantity of ammonium nitrate, you're asking for big trouble. Here.
What were they going to do with that? Where were they shipping it to? Or were
They were shipping it to farms, I think. Just this fertilizer, yeah. Fertilizer. Yeah. Well, you saw the you know, those explosions were small. Did you see the explosions in China? On the where was that? At the storage facility? Oh, you should take a look at those explosions, because those explosions were like a nuclear blast. You would think they weren't storing ammonium nitrate, they were storing some kind of uranium 238 or something. It was this huge. That was like last year. Okay. All right. Well, we'll continue the what was that? The zinc, the magnesium. We'll continue the magnesium test next time. So I'll stop here and then let you guys get started. Are there any questions though? Did you find the questions from that you had from chapter 15? No. Yeah, Anthony. No. You could do it on the product side too.
And that's only if it's like
Yeah, it depends on what direction you're going. You know, it works if the change is small. And so it depends on the direction. K has to be either really big or really small for the simplifying assumption to work. Really big or really small, and the initial amount has to be big, relatively big. And so the book comes up with a ratio. They take the ratio of the initial concentration divided by K, or K divided by the initial concentration. And if the ratio comes out to 1 to 1,000, that is, the initial concentration is 1,000 times bigger than K, or vice versa, or no, just we'll leave it at that, then it works, okay, or it should work, but it doesn't always. But you know, why bother calculating that ratio? Just try it, because it doesn't take that much time. And in calculating ratio, probably not worth doing. Okay. Any other questions? All right, we'll go ahead and get started. And then